Okay, kids, happy snow days again. It's time for us to do solids of revolution. I'm a little bit bummed not to do this with you in class because this is one of my favorite lessons, and I bring potato chips and lifesavers and all that kind of stuff, but I'll just have to bring them in at a different time. So, volume. We went area between two curves, and now we're going to do volume. The homework over the next couple days is going to be in the same section, because it's going to take us a number of days to get through all the volume. Different types of ways that we can calculate volume. So in geometry, you did volumes of cones and volumes of pyramids and volumes of spheres, three-dimensional shapes. Well, now we're going to find the volume of three-dimensional shapes, but they're three-dimensional shapes that we create. And we create using functions. So for instance, if I have a bounded area between two curves, or between the axis and a curve, and I revolve that area around an axis. And for us in this, in AP calculus anyway, the lines of revolution will all be either horizontal or vertical. None of them will be diagonal. That can come later. So there's your homework. Page 407, 7 through 14, all 21 through 22. Some of the nice things about the original problems is giving you the connection between geometry that you did back in whatever grade and how you can use calculus to generate the same answers as memorizing those, oh, the volume of a cone is this, the volume of a cylinder is this, the volume of a sphere is this. So those are nice problems. So as I said, I want you to think of potato chips, lifesavers. That's today's lessons, because I'm taking two lessons and putting them into one. Potato chips and lifesavers. Play-Doh will be in another couple days, and the same with bundt cakes. Three-dimensional shapes. So this slide is very mathy. All right, so we're going to break it down to find the volume of a solid. So you see that funny-looking potato almost shaped solid. Get it? Foreshadowing. And if you cut up a three-dimensional solid, right, you superimpose an axis on it. So there I'm putting an axis right through the middle, and I'm going to slice it up. Right, I'm going to take a knife, slice it up. Each one of these little widths is dx, right? Notice that the height of each one of these slices changes as I move through the domain. So blah, 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 eighth slab of a cylinder. So each one of these little things, if you plop it down, is like a fat cylinder. And then if you stack those cylinders on top of one another, you can approximate the area. And of course, if you sum all the areas of that cylinder, you get a good approximation for the volume. And of course, as the number of slices that you make approaches infinity, the better your approximation is going to get. So here is Riemann, and here's Leibniz. So the limit as you take delta x to 0, so that means you're making infinitely thin slices here on the x-axis, approaches 0 from your first slice to however many you need, infinity, remember? And here's the area of x stuff times delta x. So this is the important component right here. You are starting to make slices at A, over here, finishing at B, and you are summing the areas of the cylinders times their widths, right? Because the slices that you make gives it the third dimension. Area times width gives you volume. Now I have these examples. If you go to Edline, I have a worksheet with these examples on it. So let me show those to you. I have them up on my screen. So the examples that I'm about to do on the PowerPoint, 1, 2, and 3, and I have one last example that's not on here, but these are all on the Solids of Revolution worksheet that is on Edline under Handouts, with Mr. Potato Head to symbolize potato chips. So calculus books will not call these potato chip problems, they'll call them disc problems. A potato chip is, if I took a potato and sliced it really, really thinly, and of course fried them, I get potato chips. Potato chips are solid, right? There's no holes in them. And it's approximately disc shape. So, here is the square root of x. Square root of x from 0 to 4. I drew my function here, right? There's my function, square root of x. And I'm going to take I'm going to take this function, rotate it around the x-axis, spin it, if you will, and create this three-dimensional shape. And I want to find the cylinder. Oh, I'm sorry, I want to find the volume of it. So, what I'm going to do is get a whole bunch of these cylinders right here. But the cylinder is really flat, right? And it's circular. And if again you can picture clicking and dragging this green shape all the way through. This is my representative rectangle, just like I did with the area between two curves. But now I'm going to spin it. So it's as if I took the square root function, reflected, remember geometry, reflected it around the axis of rotation. Took this, it's a horrible drawing. Horrible drawing. Let's try that again. See if I can do this again. A little bit better. There's my representative strip. I go from the middle of the figure up to the function and spin. There's my potato chip. Right? Which of course is much better drawn down here than I could draw it. But it comes from this representative strip and spinning it, if you can imagine spinning down and back around. Right? And of course I can do that over here. From the axis of rotation, perpendicular, right? My slice is perpendicular to where I'm going to spin, and then spin down to the reflection, back up and around. There's my other potato chip. Here's another one. From the axis of rotation, up to the function, spin. From the axis of rotation, up to the function, spin. So I have an infinite number of these cylinders, and the area of which, of course, is pi r squared. But r is the y value of the function. Right? From the x-axis up to the square root of x. From the x-axis up to the square root of x. So each one of these is x, comma, y. But that's the square root of x. So x, comma, square root of x. Really? What is this blue height? At this particular x value, it's whatever the square root of that x value was. That's the height of each potato chip. So over here, pi times the radius squared. The radius is what I fill in with the function y. And then this part is area. How do you get volume? You take area times how thick this is, right? See that? There's the thickness of each one. But remember, the thickness comes from the slice down on the x-axis, right? Every time you change x, which is dx. So, if you take area times width, or height if you want. You know, if you picture turning this disc over so that it looks like this, right? I'm a terrible, terrible artist. Right? That's how tall, quote unquote, tall it is, or how wide it is, or how high it is. That comes from dx. Small change in x. That's how you get volume. So the volume of each disk is pi r squared times the thickness, or pi root x squared, dx in this case. Sum them all up from 0 to 4. And there's your calculus. You're going to get points for when you're setting these problems up. No one's going to give you a point for your drawing. I don't care if you come up with your, like my sad drawing or this beautiful drawing. But this drawing helps you think about your limits of integration. Pi has got to be there. Of course, you can osmosis pi out here, if you like. Your function, which is your radius, squared. So pi r squared. Here's your thickness. That's what generates the volume. And you're making potato chips from 0 to 4, right? Boom, 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 boom. All of those potato chips, an infinite amount of them, until you fill them all up. Now the calculus in this is no big deal. Square root of x squared, x to the first over 2 from 0 to 4, 8 pi. If you have a calculator and you want to multiply that times pi, make sure that you round to 3 places past the decimal, or you can just leave it as 8 pi. Exact answers are always right. If you choose to round, you must round to at least 3 places past the decimal. Now, the next example is where the axis of rotation has been shifted. So in the first problem, our axis of rotation was the x-axis, right? Which is y equals 0. This time, I've shifted my I'm shifted the axis of rotation to y equals 1. So same function, I have to know this point of intersection, and I have to be able to draw the reflection around the axis of rotation. I draw my representative strip from the axis of rotation up to the function. Spin. From the axis of rotation up to the function. Spin. From the axis of rotation up to the function. Spin. These are potato chips. Whole bunch of potato chips. My goal, though, is to figure out this time, I mean, the volume, the formulas don't change, but how can you represent finding the radius? So I say to myself, from the beginning, from Algebra 1, Algebra 2, whatever, I know that going from the x-axis up to the function is the square root of x. Okay, and I'm interested in the height. So you ask yourself, this line that I've drawn, is that too much or too little to represent my radius? And as you notice, each time the green is too long. Right? That's too long. How much is it too long by? That long. that height is constantly what? Constantly 1. So the radius that I want for this potato chip is this square root of x. Take away what? Hello, 1. This radius, the radius that I want, going from the axis of rotation up to root x, that radius has that too much from the function. The height of the function comes from the x-axis up to root x. So I say to myself, I think to find the radius is always the height of the function, take away 1, the axis of rotation. Notice that that also works when you're using the x-axis. It's just that the equation of the x-axis is y equals 0, so you would have the square root of x minus 0. Square root of x minus 0, shockingly, is the square root of x. So you can kind of sort of think of potato chips being pi. This is always, all these volumes are created by spinning, right? Spinning around a horizontal axis so far is only horizontal. But still, spinning around an axis is going to generate a circular shape. So I'm always going to have pi involved here. Pi times the radius squared, but your radius of your potato chip comes from the function minus your axis of rotation. Don't forget, though, that is all now the radius, and all of that gets squared. Can't tell you how many Algebra 1 mistakes are made with that. Then, of course, that's what I have right now is just area. In red is just area. Don't forget that to get volume, you need to add the third dimension, and that's what this is. The infinitely thin thickness of each one of these potato chips. Okay? Potato chips, your book will call these disks. So finding the volume of a solid of revolution using the disk method, regardless of where my axis of rotation is, whether it's on the x-axis or whether it's been shifted up to y equals 1, y equals 5, y equals -2, no matter where I go, this, as long as I have pi for my circles, limits of integration a and b, formula for my radius, and the squaring, pi r squared, area of a circle. Hello. .665, I just effing-ented this. All right. Now instead of having a horizontal line of rotation, we're going to have a vertical one, and it's the y-axis. So remember, the equation of the y-axis is x is always 0. Look at the function that I'm giving you is in terms of x. X is equal to 1 over root y, and I'm giving you the y values where I want you to create this shape. So the first thing, I don't know what 1 over root y looks like. So notice that I made a chart with y, comma, x. Well, I shouldn't say comma. When I put in a y, what is an x? So I'm putting in values for y. 1 over the square root of 1 is 1. I put in 2, 1 over the square root of 2, approximate. and I went to 4. And I drew this shape. So from y is from 1 to 4. From the x-axis, here is 1 over root y. It's 1 over root y. Whoopsies. So the region between the curve and the y-axis. So bounded area here. So here's the area. I'm going to take this figure and spin it not around, I'm not spinning it around the x-axis, right? So I'm not going to take this and spin it this way. I'm going to spin it this way. Right? So now I want to find volume. To find the volume, I take the area and multiply it times a third dimension, the width. Notice this time, the representative disk or potato chip is horizontal, perpendicular to the axis of rotation. So go again back here. Whoops, sorry. Notice here, my representative strip perpendicular to the axis of rotation. My function was in terms of x. My limits of integration were x numbers. And my width was created slicing along the x-axis. Think of dx as, as having a knife, right? And slicing down to a horizontal axis, be it the x-axis or another line that is parallel to the x-axis. And notice over here, now what's going to happen is I made my representative disk this way from the axis of rotation to the function, and then I'm going to spin this way. Get that area thing out of there. Axis of rotation to the function, spin to the image. Right? I drew the function, I drew the image across the line of rotation, then I drew our representative strip from the axis of rotation to the function, spin. From the axis of rotation to the function, spin to the image and back. From the axis of rotation out to the function, spin to the image and back. And now I just need to, now I have all, here are my potato chips, I need to add them all up. This time, each time I changed which disk I was changing and drawing along the y-axis, so the thickness of each one is dy. The radius comes from the function in terms of y. My limits of integration are y numbers, 1 and 4. Here's my pi, which I can leave inside my integral or osmosis it out. And here's my radius. Don't forget the radius is squared. Osmosis this out. Integrate 1 over y dy is ln y. ln 4 minus ln 1, but remember ln 1 is 0. I could see the answer if this was a multiple choice problem like this. You could leave it ln 4 if you like. I ln 4 would be fine. Or bring that 2 down. If I was effinenting this, if I was using my calculator, you can type in 1 over x, because the calculator is not going to let you do the y here, and you're going to get the same answer, I promise. This one's not on your sheet. I wanted to show you an example where somebody would give you, you're not going to come up with this equation on your own, but notice that it is x equals, this is a cooling tower. If I superimpose an axis over it, and then the curve of the tower looks like this. This is all physics, right? They know exactly where to make this hyperbolic shape, where the center of it is, to make the, the steam work and come out appropriately. If I stop this at 500 feet, right, here's the axis of rotation. I'm going to make that, I've just made that 0. Why, here's my origin. So this is still x equals 0. If I go out to the function and around to the image, there's my potato chip. This is the radius of going from the y-axis. How far out do I go? Spin and around. So when I set up this problem, notice this time I left the pi outside. I'm going to go from 0 to 500. That's the radius. Squared. 0 and 500 are y numbers. Function is in terms of y. Slicing to the y-axis, or a vertical line. I rounded the answer. The original problem said round the answer. Notice I have cubic feet there. But I wanted to show you on my calculator, even though all this stuff is in terms of y, here's the equation in y1, right? Notice I have x squared minus x stuff squared, right? So that's in y1, so when I math 9, 0 to 500, the function in y1 and dx, right? Even though these are y, I'm just, telling the calculator that I'm doing, pretending that it's all x stuff. Now the only thing I haven't done here, I have to look at y1. Remember, I have to have y1 squared. But if you look at what I put into y equals, I already put my parentheses around and squared it. So I don't have to do that. I could do, well, let me do it both ways. So this time I can just put y1 in here because, again, I've already squared it. I get an answer that doesn't match this because what did I forget to do? Oh, don't forget about pi, right? Which that often happens. And there's my answer, just rounded. So if I chose not to do that, if I had not in y equals squared it, so let me take that off. Oops. So let me delete the square there. I'm going to go over here. Oops, sorry. Now I'm going to square y1. Go ahead and multiply by pi. Ah! What did I do wrong? Oh, it doesn't like that I left that whole thing. It doesn't like that I left it blank. It's waiting. There we go. Okay. All right. So, homework problems are all potato chip problems. So, let's go now to, I'm going to continue to what would have been a second day. This would have been the warm-up, and hopefully you can see the homework. Same section, just different problems. We just picked out ones that were not going to be necessarily potato chip problems. This warm-up was a practice of potato chip problems with a different line of rotation, because over the years we found that that's the one that gives kids the most problems. As soon as I shift the axis of rotation off either the x or the y axis, it sometimes causes confusion. So I want to make sure to practice another one. So this is just a potato chip problem. And I know it's a potato chip problem because when I drew it, they're telling me I need the graph 4x minus x squared, which is this parabola here, which hits, of course, the x-axis at 0, 0. But they're asking me to look at the line y equals -5. So this is the bounded area they're talking about. We're going to take that area and we're going to spin it around not the x-axis but the line y equals -5. So I'm going to look at these points here. I'm going to draw the image here, and I'm going to take this piece and spin. Right? I'm going to take here, spin all the way around. This is a solid of revolution. Spin it. I think to myself as I'm drawing, go from the axis of rotation up to the function, spin to the axis of rotation, spin to the image, and back up. Potato chip 1. Axis of rotation, up to the function, down to the image and around. Potato chip 2. From the axis of rotation to the function, down to the image and around. And it is this radius that I need to find an expression for. Because potato chip setup, volume is taking this area, spinning it three-dimensional, which means I have a solid of revolution, so I have pi radius squared. Since my representative disk was vertical, I was drawing from the function down through the, perpendicular to the x-axis, hitting the line y equals y equals -5. I write dx, slicing down towards the x-axis. dx, which means these two numbers need to be x numbers, and they need to be the x coordinate here, x comma who cares, and x comma who cares. Blah, 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 blah. All I care about are these x numbers. So I say to myself, where does 4x minus x squared equal -5? And I do some algebra 1 here. So this is -1, and this is 5, which means over here I am starting to make potato chips at -1, stopping to make potato chips at 5. And the only thing I need to fill in here is the radius. To find the radius, I understand, again from algebra 1, that 4x minus x squared, going up to the function here, this is some x comma f of x, or y, or 4x minus x squared. That's how I get the height, but the height is measured from the x-axis. Is that too much radius, or too much to be my radius, or too little to be my radius? Hopefully you say to yourself when you answer, that's not enough, right? My radius needs more. How much more does it need? This radius needs more. How much more? This radius, right, needs more. How much more? Constantly this distance of 5. So this time, my radius was not, the function height didn't give me enough radius. I have to always add 5. So this becomes 4x minus x squared plus 5. And if you think about the formula I gave you before, where I said the potato chip formula was volume is equal to pi, your radius was always going to be your function, y, or f of x, however you want to say it, minus the axis of rotation. Well, when your axis of rotation is y equals -5, guess what happens when you put that in there? F of x minus -5, sure enough, becomes plus 5. So you can think of the formula. I generally tend to think of my drawing more. I look at the radius. Is the function height, does the function height give me too much or too little to make my radius? And then I just adjust. Or again, you can just think of your formula here if you like. So I tend to float my pi out. Here's my function minus the axis of rotation, which meant plus 5. I don't forget that I'm squaring. And now I'm good to go. Right? I can either do, this is simple enough, this could be either a calculator or a non-calculator problem. Well, I guess squared it probably would be a calculator. I got, when I was done, 814.301 pi. So, of course, you could write that as 2,558.201. Either answer. It doesn't matter how you have this answer, in terms of pi or not in terms of pi. All right, so let's go on to another volume of revolution. So the same kind of setup, except I want you to notice here, I'm going to erase all this drawing, that here was my image, here was the area that I was going to spin, and I want you to notice that the area I'm spinning completely lies against the axis of rotation. Even though the axis of rotation was shifted off of the x-axis, the shape that I was spinning lied smack up against the axis of rotation. That's going to change. I have my parabola x squared plus 1 and a linear function negative x plus 3. They intersect here and here. Okay, x squared plus 1, negative x plus 3. There's their points of intersection. I want to spin this around the x-axis. So here is the axis of rotation. Notice the figure lies, there is space. There is space here between the figure and the axis of rotation. First thing I'm going to do is find the points of intersection. Where does the linear function hit the parabola? Then I'm going to draw the reflection of the shape. So here, x squared plus x, right? Move the 3 over, move the x over here and now subtract 3. Algebra 1. So negative 2, who cares? And 1, who cares? Because all I need I'm reflecting over the x-axis. So there I drew, right? I drew the reflection of this shape over the x-axis. Here's the linear function. It used to be on top, is now on the bottom. The parabola used to be on the bottom, is now on the top. Same thing before, draw your little representative strip here. It's just now I'm between two curves. See why we did that lesson first? The area between two curves. So this is my radius. I'm going to spin from the line down to the line and back up. Then I'm going to spin from the bottom, from the parabola, down to the parabola, oh rats, and back up. That's not a potato chip. That's a lifesaver. Now, you have a bunch of lifesavers. I can create a whole bunch of lifesavers all the way through this function, or this shape, excuse me. Every time I draw a representative strip, I can make a lifesaver. Strip, spin, spin, right? A whole bunch of sad-looking rectangles because I can't. I'm sorry, rectangles. A whole bunch of lifesavers. So, how do I find the area of each lifesaver? Since I have space between the two-dimensional, right, the two-dimensional shape here, or here, and the axis of rotation, there's going to be a hole created in my shape. Right? There's going to be a hole through here. So I need to find the volume of each lifesaver, or even the area of each lifesaver. I have two circles. I have a red circle and a blue circle. So area of the big red circle minus the area of the small circle. Turn each one of those into volumes by multiplying by dx, and sum them up, and I have the volume of the big circle minus the volume of the small circle, and that's how I get my lifesavers. Now let me take away my drawings here. So there's a prettier lifesaver. I need to find the area of the big circle. So once again, there's the radius of the big circle from the axis of the axis of rotation up to which function? Linear function. This blue line is the radius of the big circle, right? From the axis of rotation up to the linear function. Then notice this green line coming in. Okay, the green line from the axis of rotation up to the parabola, that's the radius of the small circle. Pi. And look how clever we are. Capital R squared for big circle, little r squared for small circle. It was the linear function that was the height of the largest radius, and the parabola was the radius of the smaller circle. I cleaned it up a little bit, right, using my properties of integrals. Factored a pi out. Again, using the limits of integration I found through algebra. And then if it into that. Again, you can 23.4 pi, you can leave it like that, or you can multiply it out. I don't care. All right. Also, I forgot to tell you that I have another handout that has these on them. Let me show you real quick. There's a second handout on Edline. Right, the example I just did is here. And here's the second example I'm about to do. Alright, so find the volume of the region R if R is rotated about the x-axis. R is defined above by the curve y equals square root of x and below by the x-axis and the line y equals x minus 2. So notice my bouncing question mark is there because the first thing you have to decide when you're doing these problems, am I a potato chip problem or am I a lifesaver problem? How you answer that question does my shape, my original shape, before I revolve, does it lie all against the axis of rotation? And here, I hope you can see that you have two things going on. So the first thing I did was draw my image. Here's root x, here's the line x minus 2, and then I drew the image of root x across the axis of rotation, and the image of x minus 2 across. So I'm thinking about starting here and not ending until here. So I've got an issue, right? I have a bunch of stuff. This is an interesting problem. Notice that when I start drawing representative strips, right here, this part, well, I've got no space, right? The image that I'm going to spin is all the way against the axis of rotation, but that's not true past there. Right? As soon as I go past 2, oops, I didn't color all the way in, did I? As soon as I go past this point of intersection here, the image that I'm spinning is not up against the axis of rotation, which is still the x-axis, right? So I have to think about breaking this problem up. So the yellow piece goes from 0 to 2, and then this point of intersection is at x equals 4. Right, when x equals 4, y equals 2. So I can attack this problem by doing potato chips here and lifesavers here. And again, the difference is the yellow shaded area lies all the way along the axis of rotation, and the purple, there's a space between the image and the axis of rotation. That's how I know potato chips versus lifesavers. But some of you might already recognize some geometry. That's why my little stop is there. Right, here's the little representative strip I could draw through the yellow piece, and as I click and drag, I realized that, just remember when we were doing area between two curves, the top of the function, the top of my strip right now is the curve, root x, and the bottom is the x-axis. But as soon as I get to 2, that strip is going to change. The top is still defined by root x, but the bottom is now defined by the linear function. The minute your boundaries change for your strip as you go through your area, you have to split up your integrals. However, if you recognize sometimes, right, geometry comes to the rescue. Not often does geometry come to the rescue, but this time it does, because check this out. That's a freaking rectangle. And if you take a rectangle and spin it, that's one of my geometric shapes whose volume formulas I memorized. Right? That's a cone. So this integral right here represents its potato chips for the yellow area. Going from 0 all the way to 4 though. So going from 0 all the way to 4 here, and then subtracting out that cone. That's one way to attack this problem that way I don't have to deal with lifesavers. Right? I don't need a lifesavers problem. Let me do that again. I'm going to pull that back. Right? Going from 0 to 4. So pretending that I'm all the way against the x-axis, from 0 all the way to 4, which is a total potato chip problem using root x, and then subtracting out the cone. And the volume of a cone, again, I learned in middle school. Right? The volume of a cone is pi r squared, area of the base, times the height. Ooh, it's a cone, so I need to be shrunk by a factor of 1/3. Right? But if I didn't recognize that, and sometimes this was a nice shape, this ended up being something I could use regular geometry for because I had a regular shape, because the sides here were linear instead of a curve. So I have these linear pieces. I created a triangle, spun it. But if I was doing lifesavers, I didn't recognize that, or this shape, this linear, wasn't a linear function, it was some other kind of curve. I wasn't given the option. Then I would have to do lifesavers because of the space. And this time, notice I did potato chips from 0 to 2 of root x, because this strip stopped here at 2, and I was defined all by the x-axis and root x, minus the lifesavers from 2 to 4, and this is big R squared minus little r squared, because the larger radius was up to the square root function, and the smaller one was to the line. This, remember, was an alternate way of doing the problem. Sorry. So I can just, like I said, I can F and int both of these, get an answer. Oops. So there's 0 to 4, root x squared dx times pi. And I would have to subtract one-third pi r squared. Now think about my radius of my cone. Remember, if I was just my radius here, right, would just be constant, right? It would be from the x-axis up here to 2. So the radius is just 2, squared, of course, being 4. And the height This is the height of that cone that I was subtracting out. The height is also 2 units. Or uh-oh. Must have done something wrong there. Root x squared. Oh, duh. I have to go from 0 to 1, y2 squared dx minus, I forgot to do the large one. Big R squared minus little r squared. Wait, this should be a plus, yeah? Because I need to add going from 0 to 2, and then add going from 2 to 4. And then multiply, of course, times pi. Yay. Right, it was minus when I was going from 0 to 4 and subtracting out the cone. Has to be plus when I'm breaking it up into 2 separate problems. Yellow, this is yellow, and then add purple. Okay. Textbooks, I call this lifesaver. Textbooks call this washer method. I don't even know if you guys know what a washer is. It's like some kind of plumbing. Like if you plumbers know what washers are. They look like that. It's something you put in between. It's like a little metal thing that you put around, like when you're doing sinks and to connect pipes and some such crap. I think lifesavers is much better. Okay, there is a dagger here. This is the algebra that I was telling you about. Too many times there are students that in their haste and hurry think that these two things are equal. And of course we know they're not, right? That's a basic, no one taught you could distribute powers across pluses or minuses because you simply don't get the same result both ways, either distributing or not distributing. So these two are not equal, and this is another one of those things that AP will not follow your work from. If you set up a problem and do the algebra for a volume, assuming that capital R squared minus little r squared is the same as capital R minus little r squared, they will not follow your work from there. Potato chips, remember, just have the hole filled in. When there's no hole, you don't have to subtract out. Or you could think about 0 squared if you really want. Here's your potato chip method. dx, I've used dx in both of these formulas, means that you're taking your slices down perpendicular to the x-axis. Your radius formulas, be they big R or little r, have to be in terms of x, and your a and b's here are all x values. dy means you're slicing this way, perpendicular to the y-axis. All your radius formulas have to be in terms of y. Your limits of integration all have to be y numbers. But the actual formula never changes. It's pi r squared. It's a circle. You're taking a circle and you're revolving it and you're spinning it. So pi, what do you have a hole? Then you have 2 radiuses to deal with, or radii to deal with, dx. Or if you don't have a hole, you only have 1 radius to deal with. Here's another example that is also on that sheet of doing spinning an area around a y-axis. So all I'm doing is a vertical axis of rotation. So x squared and 2x, again, a parabola and a linear function. Think about Algebra 1 and Algebra 2, how many lines and parabolas did you deal with, right? But this time I'm going to spin it around the y-axis. So this is my axis of rotation. I have to draw a strip in my original shape. Notice my strip is looking at the y-axis. Okay, it's perpendicular to the y-axis, so I'm doing things dy. Horizontal slice, but I recognize that I have a hole. I know I have a hole because there is a space between the figure that I drew and the axis of rotation, right? A space between the figure that I drew and the axis of rotation. So I'm going to do this all with calculus, but hopefully you can see, once again, because I have a linear function, look what you actually could do, right? Another way I can see that I've got lifesavers instead of potato chips is when I draw my strip. The far right instead of the top, the right part of the strip is on the parabola. Spin it to the image of the parabola and around. The bottom of my strip is on the linear function. Spin it to the image. And here's the hole right here. So area is right here. Area times thickness or height means I have volume. Oops. I can factor out a pi. I cannot take this factor out of squared. Outer radius is just the larger one. Far right. Inner radius, closer to the axis of rotation. So which one's my axis of rotation is the y-axis, which function is farther away. dy